Okay, so we haven't scared you off completely. That's a good sign. You're back for more of Chapter 19 on amino acids and proteins. Actually, we covered a lot of ground in those first several slides of the chapter in the last lecture, and hopefully, although it wasn't that long a lecture, it was a good firm foundation for you to move forward here in the second lecture. So this particular lecture will focus on amino acids as Zwitterions. We brought up that idea before and hopefully addressed it enough times that at least the word's familiar now and you know what I mean by that, whether or not I pronounce it correctly. But there we have it. So this will be a follow-up lecture where we're focused in particular on those charges that we get on our amino acids. Okay, so to be more specific, a Zwitterion has an equal number of NH3 plus and COO minus groups. So the pi value, the ionization value there for nonpolar and polar neutral amino acids are from pH 5.1 to 6.3. So there we go. That's where typically you'll have the Zwitterion form. And if we look at alanine there, it's a Zwitterion at pH 6.0, so there's zero overall charge. Of course, there's a plus charge and a minus charge, but there's no net charge because those two cancel, and that's the typical state for alanine is to have the protonated ammonium and the deprotonated carboxylate in its Zwitterion. So to define that pi term that you saw on the previous slide, it's technically known as the isoelectric point, and the isoelectric point would be the pH at which Zwitterions have an overall zero charge. So for nonpolar and polar neutral amino acids, we have pH values from 5.1 to 6.3 is where they would tend to exist in their isoelectric points. So they'd be their Zwitterions. And of course, if we go below pH 5.1, if we get more acidic, then we're likely to reprotonate that carboxylate group to a neutral carboxylic acid. If we go much above pH 6.3, then we're likely to deprotonate the amino group, which is now protonated amine up until 6.3, but as we get more basic, we would likely run the risk of removing the H plus from the NH2 group and going back to a neutral NH2. Okay, and so here we're going to follow up on that idea. So first we'll deal with the acidic solution cases. So in solutions that are more acidic than the pi, the isoelectric point, the carboxylate group in the Zwitterion accepts a proton, and therefore the amino acid will still have a positive charge on the ammonium and now a neutral charge on the carboxylate group, and therefore a neutral, a positive charge overall, I should say. So alanine with an isoelectric point of 6.0 has a +1 charge in solutions that have a pH below 6.0. So we see there the normal Zwitterionic form at pH 6.0, and then we see at some pH less than 6.0, could be 5.0, could be 4.0, but whatever it is, as long as it's below that pH of 6.0, we're going to have a charge of 1 plus on the amino acid's no longer a Zwitterion because it's no longer neutral. It has a carboxylic acid group now instead of a carboxylate group, and the protonated ammonium group has a plus charge. There's no charge anywhere else on the molecule, so it's just a +1 ion. Okay, so if we consider the other alternative, a Zwitterion in basic solutions, in this case for alanine, we don't even have to go technically basic, right? Ordinarily, we'd think of pH 7.0 as neutral for water-based solution. Therefore, we'd say above pH 7 is basic and below pH 7 is acidic. While in this case for the alanine, what we have is the NH3 plus, the ammonium group in the Zwitterion, will lose a proton once we go above that pH of 6, and therefore the amino acid will now have a net negative charge. It's no longer a Zwitterion. So if we look here, when we have that pi of 6.0, we would be a neutral Zwitterion. If we're above pH 6.0, then we're going to be a negatively charged ion because at pH levels above 6.0, we no longer have that amino group protonated. So there we have it. If we were too acidic, for the case of alanine, if our pH was below 6.0, we'd have a +1 charge. If the pH is above 6.0, we'd have a -1 charge. But at pH 6.0, we would have a neutral Zwitterion because we would not have the situation where either of those amino or carboxyl groups are neutral. Okay, so hopefully we've kept it all together. So the summary of the pH, the isoelectric point, and the ionization. So if we look at this table 19.5 for the nonpolar and polar neutral amino acids, if the pH is less than the pi, which means we're in acidic conditions, the concentration of H plus or H3O plus increases. That means the carboxylic acid form is going to be favored over the carboxylate form. The ammonium form is favored over the amino form, and therefore we would have a +1 overall charge. If we're at a situation where the pH equals the isoelectric point, then we're going to have the carboxylate form, we're going to have the ammonium form, therefore we're going to have a plus and a minus, which is going to give us a neutral overall charge of 0, and we're going to be the Zwitterion that we're after. If, on the other hand, the pH is greater than the isoelectric point, we're in, again, when we say basic, it doesn't have to necessarily be pH greater than 7. We saw that with the case of alanine, that anything above 6.0 was still going to decrease that H3O plus or H plus concentration to the level where the ammonium deprotonates to the plain old neutral amino group. The carboxylic acid group is still going to be in the carboxylate form, and therefore we're going to have an overall charge of 1 minus in that scenario. So hopefully you've wrapped your mind around these different possibilities. And again, these are the easy ones, right? These are the nonpolar or polar neutral amino acids. Wait till we talk about the ionizable side chains. Okay, so here we are ready to deal with those most difficult case. So we have the ionized form of the polar acidic and the polar basic amino acids. So polar acidic and polar basic amino acids also ionize the either carboxylate or carboxylic acid and ammonium or amine group in their polar R group. So you don't only have the amino acid backbone, you also have the R group with an amine or carboxylic acid functional group to worry about. So the Zwitterions of polar acidic amino acids exist at pH values from 2.8 to 3.2. Remember, we had just the two examples there, the aspartic acid and glutamic acid. And then we had our three examples of Zwitterions of polar basic amino acids, and those exist at pH values from 7.6 up to 10.8. Okay, so looking at aspartic acid, it's a polar acidic amino acid, right? It has an isoelectric point of 2.8, so that means it forms a Zwitterion at pH 2.8. So we see at the far left there along the bottom, the Zwitterion form of aspartic acid. So at pH 2.8, we have no net charge. We have our protonated ammonium, we have our deprotonated carboxylate, and we have our neutral side chain, a carboxylic acid form. If we look at having a pH of 7, for instance, we see that in that situation we have aspartic acid with a charge of 1 minus, right? So it forms negative ions with charge of 1 minus here at pH 7. If we go even higher, where we have a pH greater than 10, we would now be in the 2 minus form. So notice at pH 7 we still have the amino group protonated to an ammonium. We have the two different carboxylic acid groups as neutral carboxylic acids, and then we have when we go up in pH to pH greater than 10, now we're so basic that our amine group is no longer protonated, but both of our carboxylic acids are deprotonated. So there we have it, our different possibilities for aspartic acid. Okay, so hopefully we'll make things a little more concrete now, discussing applications of those charges. And major application here is electrophoresis, which involves the separation of amino acids based on charge. So in electrophoresis, an electric current is used to separate a mixture of amino acids, and as you would expect, the positively charged amino acids will move toward the negative electrode, the negatively charged amino acids will move toward the positive electrode, and an amino acid at its pi does not migrate, right? If it's at its isoelectric point, then it's a neutral overall, although it is charged positive on the amino terminus and negative on the carboxylate terminus. But overall, it has no net charge, and therefore it does not migrate. And then the amino acids are identified as separate bands on filter paper or thin layer plates, depending on how you do the workup after you've done the separation. So here we see an example of an electrophoresis setup, and so there was an electric current applied to that mixture of lysine, aspartate, and valine on the left, and then as a result, the lysine moves to the cathode. So the lysine itself is positively charged, so it's attracted to the negatively charged end. The aspartic acid or aspartate form moves to the anode. It's negatively charged, so it moves to the positive end. And then the valine, being a neutral side chain, assuming we're at the isoelectric point, would stay right in the middle there, no movement. So we're able to separate those three amino acids based on their electric charge at that pH. All right, before we leave this part of chapter 19, let's have a learning check, see how we're doing with Zwitterions and those concepts. So in this learning check, you're asked to identify for those two structures which structure represents alanine at a pH above its isoelectric point, and then alanine at a pH below its isoelectric point. So clearly they're both alanine. Which one is alanine at a pH above its isoelectric point, and which one is alanine at a pH below that isoelectric point. So stop the video here if you need a moment to make those assignments. Otherwise, start us back up or continue to listen to the correct answer. Okay, so hopefully you were able to identify that structure 2 is actually alanine at a pH above its pi, because in structure 2 we have a net negative charge, and that's characteristic of having a pH above the isoelectric point, right? At the isoelectric point, whereas Zwitterion, we're deprotonated carboxylate group, protonated amino group, and anything above that pH-wise, what that means is we're going to deprotonate the ammonium group to a neutral amine, which is what we see in structure 2 there. For B, alanine at a pH below its pi, well, there we're going to have the opposite thing happen. We're going to be at a pH that's fairly low, and therefore we're going to have a relatively high amount of H plus or H3O plus present. So we're going to protonate the carboxylate group back to a neutral carboxylic acid, but because there's lots of H plus around, we're going to also continue to protonate the lone pair on that nitrogen of the amino group to have an ammonium group, and we're going to be positively charged like we see in 1. So there you have it. Hopefully you were able to identify that correctly on your own. If not, hopefully the explanation has helped. Certainly some additional practice and reaching out to me should help clear up any lingering concerns.